So, welcome student to Introduction to Nonlinear Optics and its application course. Today we have lecture number 46. In the previous lecture we have started important concept third harmonic generation, which is basically the continuation of the third order effect, and this third order effect also contain few other important phenomena. Cell phase modulation is one of them. We also discussed this cell phase modulation in detail, but today we will going to learn more about the third harmonic generation process, where if you launch an electric field with frequency omega, then it will give rise to another frequency of 3 omega. It is exactly the same process that we have in second harmonic generation, where it was a second order effect and we are getting a frequency of 2 omega. Here we will going to get a frequency of 3 omega instead of 2 omega, because it is a third order effect. How we are getting this 3 omega frequency we have discussed, but the evolution of the third harmonic wave is still there. So, today we will going to learn that, and also the corresponding phase matching conditions. So, what should be the phase matching of third harmonic generation, that we will going to learn, which is very much similar to the second harmonic generation process. Well, in third harmonic generation, as the figure shows, this is the old figure I am using several times, that when you launch an electric field with this particular form, then what happened, that this electric field will enter into the system, and we know that for chi3 effect, P nonlinear is equal to epsilon 0 chi 3 and then E cube. So, when it is E cube, then the electric field will be total electric field here, whatever the electric field is launched will be cube, and when it is cube, then we know that there will be two different frequencies that can have into the system. One is omega and another is 3 omega. So, the frequency that is related to omega is giving us optical Carr effect, and the frequency which containing 3 omega, that gives us third harmonic generation. So, optical Carr effect leads to cell phase modulation, and change of refractive index are there because of these effects. So, we have already discussed these issues. So, third harmonic generation is a part that we will discuss today, as I mentioned. Okay. So, equation of the third harmonic wave that we derived in our last class. So, the derivation is almost same the way we have derived the second order effect or the second harmonic generation, but only thing that you need to note here is the phase thing. This is a phase term, and for this phase term we have k 3 minus 3 k 1. For second harmonic generation, if you remember, it was k 2 minus 2 k 1. K 2 was the corresponding propagation vector for second harmonic wave, and k 1 was the fundamental wave. Exactly the similar way here, k 3 is the wave vector for third harmonic wave, and k 1 is the fundamental wave. So, here in the left hand picture you can see that electric field E 1 is launched with a frequency omega. Inside the medium where we have the third order effect, E 1 and E 3 will going to generate, E 1 with frequency omega and E 3 with frequency 3 omega, and when they will going to generate, there will be some differential equation that should govern the evolution of these two waves, and these are the two differential equation which are coupled to each other as usual, and they will basically tell these two equation basically govern how E1 and E3 will going to evolve. Please note that at the input at this point where Z is equal to 0, E3 was not there. So, E3 is equal to 0. So, boundary condition is that when I launch the electric field E1, at the input there was no third harmonic wave, because the wave will enter into the system and then the dipole will start oscillating at 3 omega frequency, and then gradually the third harmonic wave will generate. So, that is why at the input there should not be any kind of third harmonic wave. Well, the intensity and electric field relation is also given here. Now, let me go back to the phase matching equation. If you look carefully to these two coupled equation, you can see that there is a term sitting here in the phase, and this is a usual term that we always have in this kind of equations. In second harmonic generation process also we are getting this kind of terms, and for third harmonic wave also this term is there. Now, in order to have a phase matching condition, we know that this delta k has to be 0. So, if this delta k, that means the phase mismatch between the third harmonic wave and the corresponding fundamental wave are 0, then delta k is 0, basically gives us a condition that K3 has to be equal to 3 K1. Now, K3 is the propagation constant of the third harmonic wave. So, if I write K3, so it should be 3 omega divided by C multiplied by n at 3 omega. Because the third harmonic wave contain a frequency of 3 omega, we write here 3 omega frequency in this place. In the similar way, K1 should be here, again a typing mistake, it should be K1. So, K1 is supposed to be omega divided by C, then multiplied by n of omega. Omega is a frequency of fundamental wave whose corresponding wave vector is K1, and n of omega is a refractive index at the frequency omega. So, now if I equate these two things, readily you can find that we have an expression that n of 3 omega has to be equal to n of omega. It is a similar kind of expression that we have for second harmonic generation. Only thing is that the frequency here is 3 omega, in that case it was 2 omega. So, now we need to find out the way how to make this n of 3 omega to n of omega. Some birefringent process can still be possible to do that. So, we will not going to discuss in detail, because we have already discussed this phase matching issue in the second harmonic generation process. Now, the next thing we need to know the evolution of the third harmonic wave. So, we know that the third harmonic wave is evolving. So, this is the third harmonic wave that is generating. So, we need to find out the evolution of this wave, how it will going to evolve over z. This is the distance, this is the distance, and this distance is z. So, we need to find out how this will going to evolve, and to understand the evolution we have two equations in our hand which are coupled to each other, and this is our equations, these two our equations for E1 and for E2, E3. Now, here the condition is the non depleted pump. That means, we launch a very strong pump, and this strong pump basically generate, this is a source term to generate the E3 wave or the third harmonic wave. So, since E1 is very strong, so certain percentage of E1 will be there to generate the frequency 3 omega, the field with the frequency 3 omega. So, we can consider E1 as a constant. So, once we consider E1 is a constant, then it is very easy to solve this equation. So, we know that from our second harmonic generation process, the study of our second harmonic generation process, once we consider the pump is very strong and it is constant, then the equation become quite simple and the integration is very straightforward. So, now if I integrate this equation, this is my equation now, because I want to find out the evolution of E3 and E1 is constant. This is not a function of Z. So, if this is not a function of Z, then the integration is straightforward, because other term is not containing any kind of Z, only term that we have Z is delta k Z. So, once you integrate this quantity with the boundary condition that E 3 at z equal to 0 is 0 and E 3 at z equal to z is some quantity, say E 3 z. Now, if I integrate these things, as I mentioned, this is a constant, so it will come out from the integration, only I will going to integrate this quantity. It will be as usual e to the power of minus I delta z divided by I delta z with the boundary condition that 0 to z. We put this 0 to z and we can write it is e to the power minus I delta z minus 1, because at z equal to 0 it is 1, divided by I delta k with a negative sign. We can further modify this expression and we will have this equation, and then finally, we will come to a point which is quite similar than that we have in our second order effect, this term. This calculation is quite straightforward and I am not going to give you all the detail, because all the steps are here. When you do this calculation by yourself, you can readily understand that how these things is happening, how this sine term is coming, this small manipulation is there. So, this is a very old calculation that I am basically using. Now, after having the expression like this, so this is the P3, mind it, every time when we deal with the electric field, it is then converted to the corresponding power. We know the intensity of the third order wave is related to this expression, half of epsilon 0 n 3 c mod of E 3 z square. E 3 z is now in our hand, this is our E 3 z. So, once we know this is my E 3 z, so I will make a mod square of that. When you do the mod square, this exponential term will cancel out and only this term will be here. So, it is here, and since I am calculating the corresponding power, one additional half epsilon 0 n 3 c, this term will sit here within area A, because power is basically area multiplied by the corresponding intensity. Now, this is a sinc kind of function. So, sin x square divided by x square. So, if delta k is not equal to 0, so we will have a similar looking curve that we already got in our second. So, we will have the power change at this. So, this is at delta k equal to 0 point. So, at delta k equal to 0 point, we will have a maximum power, and then if delta k is not equal to 0, we have a window which is called the bandwidth. For this bandwidth, we will have some kind of energy. Anyway, so this is all these things we already know. So, now the next thing is to find out the corresponding efficiency. If I try to calculate the maxima of these things, as I mentioned, the maxima will appear at delta k tends to 0 point. When delta k tends to 0, this sin x sin square delta k z by 2 divided by delta k by 2 whole square, this function will simply be z square with the limit delta k tends to 0. So, delta k tends to 0 is nothing but the phase matching condition. So, that means the maximum power that one can have is P 3 max with the condition that phase matching is there, that means delta k tends to 0, and if we look carefully there are a few terms there, but the dependency is z square, which is important. That means the power of third harmonic wave will increase as a function of z with a square form. That means it will increase with a z, and this increment is in parabolic in nature, it will be a square form. So, this dependency again we already know from our previous experience when we deal with the second harmonic generation. This is something like the same thing, that it is evolving as a function of z square. So, now look at this curve. If I now plot the efficiency is nothing but the ratio of the power that is generating divided by the input power. So, this is the quantity we can define as efficiency, and now we write efficiency max, that means maximum efficiency I am talking about. So, whenever I talk maximum efficiency, that means I consider delta k is automatically 0. So, under that condition we have an expression like this, and this efficiency suggests that the energy of the third harmonic will increase as a function of z in this way. Now, as I mentioned, this is really true when the conversion efficiency is really very small. So, whatever the drawing we have here, so please note that we have already reached to 100% efficiency, and if I go z equal to 10. So, if I normalize this fact, then we can see that the efficiency as if it is reaching the value 100. That means huge amount of energy conservation can be possible, but this is obviously a non-physical argument, because efficiency cannot be reached monotonically, cannot be increased monotonically, because the one very important assumption we consider here is E1 is constant. So, the energy E1 is a field, is constant, is a important approximation that we consider. So, E1 is not in the physical sense, it should not be a constant quantity. So, it will also decay. If it is decay, then we need to do a more careful calculation to find out how the power of third harmonic will going to evolve as a function of z. So, for small efficiency maybe it is true, but if I increase the value of the efficiency, then we need to consider the condition that E1 is also going to decay. But here in this approximation or this calculation, we consider E1 as a constant, which is not very much true for real case. Now, we start the another condition that we consider that the electric field containing frequency omega, which is the fundamental electric field, or E1, is no more a constant quantity. So, we will going to take care of both the equation together. In the previous case we considered this is a constant quantity, but we will not going to consider this anymore. So, we will consider both the equation together. So, we try to solve the coupled equation. So, to make life simple, we consider delta k equal to 0, that means with the absolute phase matching condition what happened. So, this equation basically simplify with these two form. Kj is basically the coefficient that will contain all these terms 3 by 8 kappa 3 omega c n 1. This is a constant term. So, we remove this constant term with a smaller coefficient called kappa 1 and kappa 3. This is a coupling coefficient also, because this coupled one field to another one. Now, once we have a simpler expression, this next thing we need to do is to calculate the amplitude and corresponding phase separately, because we know that E1 is a called complex amplitude. E1 has a complex quantity, E1 is a basically complex quantity. It should have an amplitude, also a phase. So, in order to understand how the amplitude and phase will vary, we just divide this total electric field, which is a complex electric field, into two parts. One is amplitude part and another is the phase part. And we know that any complex quantity can be represented in terms of r e to the power I theta. So, exactly that we are doing here. We write one amplitude part and another phase part for both the cases. Now, here E1 and phi 1 both are real, because we just divide these two things to real and imaginary part. So, E1 and phi 1 has to be real. In the similar way, E3 and phi 3 are real when E3 and phi 3 corresponds to the field E3. So, U3 phi 3 is real, and we divide the total field into amplitude and phase part, and that is our form. Well, once we have this form, next this is our equation, coupled equation, and this coupled equation basically this is our solution. For this solution, I mean, I want to put these things into my coupled equation. When I put this thing into coupled equation and separate the real and imaginary part, so we will have a set of equation, amplitude equation like this and set of phase equation like this. Please note that when you put this E1, so U1 and phi 1 will be here, and in the right hand side also you will have U1 and phi 1, and now we will have a equation where real part and imaginary part in the left hand side and right hand side also have a real and imaginary part. If I separate out the real and imaginary part, then we can separate this amplitude equation and phase equation. This is the treatment that we have already done in the second order effect. So, I ask the student to please do that by yourself and try to find out whether you are getting this amplitude and phase equation by yourself or not. The expression is already given in this slide. Well, once we have the amplitude equation and phase equation, you may carefully look that there is a quantity psi is here. Psi is the phase difference, and this phase difference between these two is defined by this. It is phi 3 minus 3 phi 1. It is something like k 3 minus 3 k 1 like kind of things. So, we will have a two compact equation, phase equation and amplitude equation. The similar kind of treatment we have done in the second harmonic generation, all the details are there. Now, once we have these four equation in our hand, then we can define one quantity which is constant over motion, and this constant over motion quantity is called the gamma. If you remember, for second harmonic generation case, this gamma constant of equation motion was u1 square u2 cos of theta, where theta equal to phi 2 minus 2 phi 1. It is exactly the similar kind of expression that we have right now, but instead of having u1 square, we have u1 cube, and u2 is replaced by u3 because u2 was a field corresponding to amplitude of the field corresponding to the second harmonic. Here we are dealing with third harmonic, that is why the nomenclature is different. It is now u3. So, once we have this expression, we consider this as a constant, try to find out whether this is really constant or not. So, what we will do, we will just make a derivative with respect to z both the side. When you make a derivative with respect to z, then the right hand side you write 3 u1 square, because u1, u3 and psi both are function of z. So, first there will be 3 functions, so 3 derivative will associated with that. So, first is 3 u1 square u3 cos psi and the derivative corresponding to u. Second term is derivative corresponding to u2, and third is the derivative corresponding to psi. So, psi is equal to phi 3 minus 3 phi 1. So, obviously, del psi del z can be represented as del phi 3 del z minus 3 del phi 1 del z. So, exactly these things are here. So, we just expand the expression of phi, so that we have all our terms like this, and this. All the 4 terms in the left hand side is given. If we put all these 4 terms, whatever we have in the left hand side, we can readily find that this quantity is a constant quantity. So, once we have this is a constant quantity, then we can see that u1, u3 and cos z is a constant, this is a constant of motion. That means, if I change both all these things, 3 functions are function of z, but they are constant over the z. That means, whatever the value of this function at z equal to z, it should be same at z equal to 0, because they are constant. So, if I put z equal to 0, then u1 cube u3 z, u1 cube u3 cos psi at z point is equal to u1 cube u3 cos psi at 0 point. So, if I put this 0, then one term is appearing here, which is u0, u3 0. Now, u3 0 is nothing but 0, because u3 is the amplitude of the third harmonic, and we already mentioned that when we launch an electric field E1, there was no, at z equal to 0, there was no E3. So, E3 is also 0. So, at z equal to 0, E3 0 means U3 at z equal to 0 is 0. So, entire quantity here is 0. So, now we have a very interesting expression. This is exactly the same treatment that we are doing, we have already done in our second harmonic generation. Well, so this is the expression that we have, and from here we find that this quantity is 0, u1 and u3 are changing. So, cos of psi has to be, the phase relationship has to be some constant value, and if it is 0, then it leads to one fact that psi is equal to plus minus of pi by 2. Then only we have this quantity is equal to 0. Once we put psi equal to say plus pi by 2, let us put plus pi by 2 first, then this amplitude equation is now simplified with this and this. So, this phase term or psi term will vanish, because sine of pi by 2 is equal to 1. So, this term will just vanish, and instead of this term we have 1. So, we will have 2 things in our hand, 2 expression in our hand, and this is the modified amplitude equation. So, using this modified amplitude equation, we will try to find out how u1 and u3 will going to evolve, and that we will do in the next class. So, let me conclude, because our time constant is there. So, let me conclude my class here. Thank you for your attention, and see you in the next class to understand the third harmonic generation in more detailed way. Thank you.